So 6.7, we're finding inverse functions. Inverse are, think of it like reversing a function, okay? What do I mean by that? Well, if we look, let me find a spot here to draw a little diagram. That's a good spot for a diagram. If we look at a diagram of this, I showed you this before back in section 2.1 when we first really introduced what a function was, okay? I said that if we have some function, I write it like a box, so it's just some magical equation that changes stuff for us. And if we take a number and I put it into the function, that's my input, right? Those are our x variables. So with that input, the function does its magic, and then it spits out an output, or a y variable, right? Okay, well, all we're doing for an inverse is that we are reversing that. We are literally taking these outputs, and we now want to call them inputs. And we are putting it back into the function backwards, and then spitting out new outputs, okay? The old outputs become our inputs, which then reverses the process, and so then the old inputs are now our outputs. It's literally reversing the process, okay? So that is essentially what we're doing here in finding inverses of functions. So, I've been saying function, but actually you can find inverses of all relations, okay? Remember, a relation is simply where you can pair things up. These x's give me these y's, okay, if we're talking about x and y graphs, okay? But remember, what's specific about a function? What makes a function different than any other relation? Do you remember that? Anybody? No. A relation is a function if one input gives you one output. Okay? That is what a function is that if I plug one number in, I'm going to get only one number coming out. Okay? That makes a function. So, I can find inverses of functions, but I can also find inverses of relations. Okay? Now, what it does, and they kind of explain it here, but a little confusing, I think, because they say, if a relation pairs element A of the domain with element B of the range, all they're saying is if A is the x and B is the y, we get a point AB, right? Well, then the inverse of that function, or that relation, would switch those around. That same point would instead be mapped to BA. Notice, the x-coordinate became the y-coordinate. The y-coordinate became the x-coordinate. We just switched the x and the y. Take a look at it in another way. All right, so let's focus on relation A. Or I'm sorry, this is relation R. So relation R. First off, they're calling it a relation because we haven't specified is it a function or not. What do you think? Looking at that mapping, is that a function? Yes. Yes, because one input gives us only one output, right? It doesn't matter that two different inputs give us the same output. That doesn't matter. What matters is I took one number and I got out one number. Okay? So yes, this is a function. Okay? And I could then, if I so chose, I could write this using function notation. If I knew the equation of this particular function, I could say r of x equals whatever that equation is, right? Why did I say r? Because they called it relation R, right? Okay, so I could use that notation, because remember, function notation is only used if you're actually dealing with a function. Okay, well, the inverse of this, we very literally take the inputs, our domain, and they become the outputs, our range. You just flip them, switch them, okay? The range becomes the domain. So remember, domain means x, range means y. So our x values became our y values. Our y values became our x values. But everything else stayed the same, meaning 1.2 and 1 were attached, right? Well, looking at the other one, 1.2 and 1, they're still attached. It's just now it's in reverse order. 1 gives me 1.2, rather than 1.2 gives me 1. See what I'm saying? Okay, so all we're doing for an inverse is we are switching the domain and the range. We're switching the x and the y. Okay, but take a look at that relation there. Is the inverse a function?
No.
No. Very good, because one number going in is now giving us two numbers coming out. Okay, so this one is not a function. But there is a notation for inverses. And I'll be the first to admit, it can be confusing. Okay, remember how confusing function notation was to you guys at first? Where you saw that f of x and you're like, well, does that mean f times x? And I kept saying, no, it doesn't. Okay, and you guys are hopefully now getting used to that, where r of x means a function r where x is the variable, right? That's what it means. It doesn't mean r times x. Well, inverse function notation is also confusing. So you have to really pay attention and really understand what context you're working this in, okay? We are working with equations. We are working with functions. Therefore, function notation means a certain thing. Okay, I've built it up enough. Here is the inverse notation. If I want to write, knowing that I have the inverse of a function, right? I would say the inverse of function r is written this way. R to the negative 1 power x. It doesn't mean r to the negative 1 power times x. It means r inverse of x. It's the inverse of the r function. Catch what I'm saying? Okay, so as you see here that I used it, if you see an inverse of a function, that does not mean it's necessarily a function. It could be, right? But it doesn't have to be. Because in this example, our relation here is not a function, but I still use this notation. Because all this notation says is that we have the inverse of a function. This function over here. Okay? Okay, so let's continue on with this idea of finding an inverse, and let's go ahead and find an inverse. Let's do an example. So let's take a look here at problem number 1. So on problem number 1, they give us a relation. They want us to find the inverse of that relation. So, inverse of S. All right, so they give us x, y, like basically a t-chart, right? They give us a t-chart. So I'm going to write my answer as a t-chart. Please remember that all you're doing for an inverse is you're taking your x, those become your y. You're taking the y, those become your x. You're just switching what they are. So, what am I going to write down in my t-chart for the x's?
Negative 1, 0, 2, 3.
That's exactly what I want to write down. Okay. What am I going to write down for my y's?
0, 2, 3, 4.
So we now know what the inverse relation is. We haven't talked about a function or anything like that yet, and we really don't need to at this point. They didn't ask us, is it a function, is it not? Okay, but we have the original relation, and we have the inverse of that relation. Okay, let's see what this looks like graphically. Okay, let's graph these two guys. So right below there is a graph And I want to take a moment to graph the two of these. So I'm going to graph the original relation using little x's so I can tell the difference. If you have colored pencils or something, go ahead and use different colors. That's fine. Put one of them in pencil and one of them in red pen. I don't care how you do it, okay? But you can go ahead and separate the two, okay? I'm just going to do one with x's and one with dots, okay? So in graphing the original relation, my first point, remember that a table of values gives me these as points. That's all these are. It's a point. So I'm at 0, -1. So 0, -1 is right there. Then I'm at 2, 0, 3, 2, and 4, 3. All right, so there's the first relation graphed. Now I want to graph the inverse of that. So again, these are simply points. So I'm at -1, 0, 0, 2, 2, 3, and 3, 4. So I've graphed both now. Okay? Well, let's take a look at that graph. Looking at that graph, do you happen to see anything special going on here between the original and its inverse? It looks the same, except what does this motion mean? Getting folded over, we call that a symmetry. Symmetry, it is a reflection. Okay? Yeah, it's a reflection symmetry. Okay? So, can you also, if you just use your imagination, can you see the mirror? Can you see where the line would be that it's being reflected about? Yeah? Well, that line, hopefully everybody is seeing it here. That line is sitting right here. And it should be a straight line, so if you draw this in, please don't be sloppy. And it is a line in a specific location at y equals x. It's at y equals x. If I look at any point on that line, like say this point here, my x coordinate and my y coordinate are the same thing. So that's another way if you're unable to use a straight edge for some reason, then you could just go through and say, okay, where is 0, 0? Where's 1, 1? Where's 2, 2? Where's 3, 3? Where's -7, -7? Right? And draw your line through those, because it's at every point y equals x. That's the equation of that line. So, why is that? Why is it at that y equals x? Why is that line important? And does that work every time for every inverse? Well, first off, the answer to that question is yes. Every single relation or function, if we graph it, the inverse will be the mirror image of it about that line. Why? Well, because if we look up here, what did we do? We said that these x's equal these y's. We said that these y's equal these x's. And so we are the ones, well, actually the definition of what an inverse is the ones, but we're the ones that did that. We're the ones that said, hey, x is here equal to y's there, which is why it's being reflected about that line, y equals x. Okay? Every single inverse will be the reflection of its original function about that line. So that tells us certain information. Let's take a look at our notes over here. I apologize here. I have these two little other paragraphs kind of flipped around, so we're going to go and we'll go in the same order, but I should have had them flipped, but that's beside the point. Looking at this top paragraph, it says, as shown in problem 1, the graphs of a relation and its inverse are the reflections of each other in the line y equals x. If you describe a relation or function by an equation in x and y, you can switch x and y and get the equation of the inverse. That last sentence holds a lot of power. Highlight that, underline that, Look at it and remember it. If you're given the equation of a function or the equation of a relation, you can find the equation of its inverse by simply switching the x and the y variables. That's what they're saying. It's the same thing we did with the table of values. It's the same thing we did graphically. We reflected about y equals x. So it's the same thing we're going to do with the equations algebraically. Okay? So, and I'll show you an example of that. I do want to talk quickly, and I've already said this, but I want to have you write it down again. For the notation for an inverse, please first off remember function notation, f of x. That can only be used when you have a function, right? So if the book or an assignment or a test says f of x equals some equation, you know positively 100% without a doubt that that is definitely going to be a function. Why? Because they told you so. Because it says f of x equals, or g of x equals, or whatever they want to call the function. Okay, we've dealt with that. Comfortable with that? Seen that? We've done a lot of function notation stuff in the last couple of sections. But the new notation for inverses, again, this gets kind of confusing. The new notation, f inverse of x, may not be a function. Okay? It could be, but it doesn't have to be. All that notation is saying is that that equation is the inverse of a function. That the original equation was a function. Catch what I'm saying? That's all it's telling us. Okay, it's telling us that the original was a function. So, for example, if the original equation was a relation, not a function, then when I find the inverse, I wouldn't use this notation because the original wasn't a function. So therefore, the inverse isn't the inverse of a function. Catch what I'm saying? Might have lost you on that one. Okay? All right? You only use this notation here if the original equation was a function. That's maybe a better way of putting it. Okay? All right. So, let's take a look at our example down here. Finding the equation of an inverse. We are given a relation. Okay? And by the way, looking at that relation real quick, is it a function? We're going to do more of this next week where we have to look at it and decide if it's a function or not. What do you think? Is this a function or not?
Yes.
Yes.
Why are you saying yes? Are we just guessing or do we actually have a reason for it?
Because f of x, if it has like a negative x, not going down.
No, yeah, we got to look at just the equation given to us. Y equals x squared minus 1. Ah, you're going graphically, and that's fine to think graphically. Okay, she's saying,
Does negative 1 squared equals 1?
nope, she is saying that if I went to graph this, this is a parabola, and actually it's a parabola shifted down one. It's a parabola shifted down one, and it would look like this. And that parabola passes the vertical line test. So it is definitely a function. Okay? Another way that you could think about this is simply by looking at the equation and saying, okay, if I take a number, pick a number. You don't all have to pick 5. Pick anything you want in your head, square it, subtract 1 from it. What'd you get? Okay. Other people might have gotten something else, but you know what I'm saying? But how many answers did you get? 1. For one thing you plugged in, you got one thing coming out. And you can pick as many numbers as you want and try that with. Every time you do it, you're going to get one thing coming in, one thing coming out. So it is a function. So therefore I could, if I wanted to, rewrite this as f of x equals x squared minus 1. Because it's a function, so I'm allowed to do that. Correct? Correct. Okay. So, next, we actually need to find the inverse then of this function. So to find the inverse, you literally switch the x and the y. Now please think of it as switching, not moving. I had some issues with that in an earlier class period where people thought I was moving stuff around. I'm not moving anything. I'm switching. I'm switching all the y's I see into x's. And I'm switching all the x's that I see into y's. So I'm going to rewrite this equation as x equals y squared minus 1. So now that we have our inverse written, in fact, this equation is the equation of the inverse, but it's not written in the form that we like to see stuff. We always like our equations to be y equals whatever we get, okay? We always want them to be y equals. And so we have to rearrange this equation. My first step right now is going to be something that you don't have to do. The only reason I'm doing it is because oftentimes you guys are used to seeing what we're solving for on the left side. All right, we solve stuff and we get x equals 7, or we solve stuff and we get y equals 13, right? We write our equations, we say y equals 4x minus 2, all right? The stuff that we're solving for is always on the left side. So for this first example, I'm going to leave it on or move it to the left side. And so what I'm going to do is I'm going to flip-flop my equation. Please stop me if anything is confusing. I'm simply going to rewrite this as y squared minus 1 equals x. I just flip my equation around. Is that okay? Good. So now I need to get y by itself. So what's my first step? Add 1. So y squared equals x plus 1. And again, I got to get y by itself. I don't care what y squared is. I want y. So what do?
Square root.
I square root both sides. Very good. Now, this is a callback to Unit 1. It's also a callback to earlier in this current Unit 5. We put in the square root. We get 2 answers. Y equals positive and negative square root of x plus 1. That is not only true for square roots. It's also true for fourth roots and sixth roots and eighth roots. Any even indexed root, right? If I was taking a cubic root, I don't do anything. Cubic roots have 1 answer. Okay? Seventh roots, 1 answer. Okay, but any even index, you get 2 answers. Okay? So, we have now found the inverse. Okay, so yes, that's it. We've found that. Okay, but again, I'm trying to get you guys used to the notation. Right? So I could, if I wanted to, use my inverse function notation. Now again, I've said this before, I'm only using this notation because the original relation was a function, right? The original one was a function, so now I could say that the inverse of that function is positive and negative square root of x plus 1. Okay? This inverse notation is only used when the original equation is a function. Okay? All right. Well, next, and again, we're going to do more of this next week, but I want you to get used to it now and see it now. We already said that the original equation was a function. Well, what about the inverse?
It is not a function.
Why is it not a function?
Because it doesn't pass through the y-test because it's on the side.
Okay, very good. Think of it graphically, and we'll get more of that here in a little bit. But what other reason do you think?
It's positive and negative.
When you plug in one number, you get 2 numbers coming out. If I plug in 3, if I say x equals 3, that means I get positive and negative square root of 4, so my answer is positive and negative 2. I put 1 number in, I got 2 numbers coming out. So this is not a function. Let's take a look at one more example here. So, Going right next to that guy, we want to know what is the inverse of y equals 2x plus 8. So what is the first thing we do to find the inverse? Switch the x and the y. So that means we have x equals 2y plus 8. And now we want to solve for y, right? We want our equation written properly for us. So we're going to subtract 8 from both sides. Now notice I didn't flip-flop the equation. You can, but you don't have to, right? You can if you want, but you don't have to. So I have x minus 8 equals 2y. Now what am I going to do? Divide by 2, right? Okay. So I do not want y equals x minus 8 all divided by 2. Okay? Why not? Because actually this is a line. This is a line. And I like lines written in y equals mx plus b. Now, how do I know it's a line? Because the other graphs we dealt with were absolute values, which had an absolute value around the x. And the other graphs we dealt with were radicals or square root functions, which had a square root around the x. And the other functions we dealt with were parabolas, which had the x squared. And the other graphs, they weren't functions, but they were graphs that we dealt with, were circles, which had the x squared and the y squared. Well, this only has an x, not an x squared, not an absolute value, not a square root, and the y is not squared, so this must be simply a line. Catch what I'm saying? It's really, to identify what it is, it's really a process of elimination. There's no absolute value, so it's not a v. There's no square root, so it's not an arc. There's no squared for the x, so it's not a parabola. And the y's not squared, so it's not a circle. So it has to be a line. With me? Okay. Well, I like my lines written in slope-intercept form. So therefore, I'm going to break that apart. I'm going to say that this is x, oops, let's get a different color here. This is x divided by 2 minus 8 divided by 2. Okay? X divided by 2 is the exact same thing as saying 1/2 x. 1/2 times x is the same thing as x divided by 2. Yes? Yes. And then what is 8 divided by 2? So I would write my answer. Now I would flip it around because I always like to have it in the right order. Y equals 1/2 x minus 4. That is the inverse of the original. Okay? And just for practice, is the original a function? Y equals 2x plus 8?
Yeah.
Yes, it is a function. So I could write f of x equals 2x plus 8. So therefore, I could write my inverse as f inverse of x equals 1/2 x minus 4. And quick question, is the inverse a function? Yeah, in this case it is. Okay.